Okay, so as I was saying, L is 2 pi IF, where L is the angular momentum, and I is the moment of inertia, a measure of how far mass is distributed from the axis of rotation, and F is the rotation frequency, how many times per unit time the thing is spinning around. So, if I am standing here, when is my moment of inertia bigger? When my arms are outstretched or when I hold them to my side? When is I bigger? Outstretched, because then mass is further from my axis of rotation, assuming I'm going to spin around like this. Okay? So, I is bigger when you have mass on the hole further away from the axis of rotation, smaller when it's closer in. And so then the demonstration, of course, is when I sit on the cart. Oh, why not just sit on the cart, right? Keep things lively. So, sit on the chair. Do I have it in here? Yes, I do. Look at that. All right. So. Now my wife can see on video when I kill myself falling off. And she'll say, I knew I should have just asked him never to do that again. But anyway, so, high moment of inertia. I start spinning. I pull the weights in. My moment of inertia, my I goes down. And as a result, my F goes up, and vice versa. Right? So, one more time. Big I, small f, small I, big F. So there is, we say, conservation of angular momentum, which says that if there are no externally applied torques on the system trying to make it spin faster or slower, and that applies for a collapsing interstellar cloud. It's not interacting very much with the outside. We'll have conservation of angular momentum. Its L will stay constant. Because remember that physicists, when they say conservation, mean stays the same. Similarly, that chair has very little friction. So therefore, there's not much in the way of torque applied by that chair. There is some, that's why it would slow down if I didn't do anything else. So, to a good approximation, my angular momentum, my L stayed the same. So, if L stays the same and I goes down, what does F have to do? It has to go up, right? If I times F times 2 pi is staying the same, but I is going down, F has to go up in order to compensate. And so, that's why I spun faster when I brought my arms in. That's why skaters can do that trick of bringing their arms in and spin a lot faster as a result of that. And in a interstellar cloud collapsing to form a protostar, starts out big, ends up small. So it starts out with a large moment of inertia, it ends with a much smaller moment of inertia. So what has to happen to how fast the cloud is spinning? Has to, if I goes down when it shrinks, F has to go up. So what I was doing is similar to what the cloud does. As the cloud shrinks, its I goes down, but its L, its angular momentum, stays the same. So how fast it's spinning, how fast it's rotating, has to go up. And that's what makes the disk form, and so forth. Yes?
What did you mean when you said that the interiors of stars aren't well
mixed? Yeah, the interiors of stars are not well mixed. What I mean is, well mixed would mean the whole star was convective, because convection is a kind of stirring. But in fact, stars are only, except for the very lowest mass stars, stars are only convective in part of their interiors. For high mass stars, it is the core alone that is convective. So here's a 7 solar mass star. The core is convective, but the outer layers are radiative. 3.5 solar masses, same deal. But for a 1 solar mass star like the Sun, now the outside is convective, but the core is radiative. And it's only for the very low mass stars, like 0.2 solar masses and thereabouts, where everywhere the star is convective. So when I say the star's interiors are not well mixed, I mean you don't stir the whole star by convection. And that's really important because remember that stars become giants because of shell fusion, because of fusion in a shell surrounding a contracting and heating inert core. Well, shell fusion occurs because the star has unburned fuel surrounding the core. If the star stayed mixed, it would just steadily burn its entire supply of hydrogen and never come into a stage where the core ran out of hydrogen and the rest of the star still had hydrogen to burn. If there was mixing going on, then fresh fuel would keep getting stirred down into the core, and the core wouldn't run out of fuel before the rest of the star did. And so, as a result, the Sun will be a giant someday because there will be a time when the core runs out of hydrogen, but there's unburned fuel surrounding it, and when the core shrinks, that unburned fuel will burn very brightly and cause the outer layers to swell up, etc., etc., etc. So that stars can become giants is directly tied to the fact that they are not well mixed. In fact, the Sun will waste about 90% of its nuclear fuel. It will never burn about 90% of its hydrogen. Whereas if it were thoroughly stirred, it could burn all of it. It would also live a lot longer if it could do that too, because then it would have more available fuel. Yes?
Can you explain why the shells expand?
Why they make the outer layers of the star expand? Yeah, so be sure you understand that what goes on is that the core shrinks and at the same time the outer layers expand. So contraction of the core is associated with expansion of the outer layers and vice versa, in fact. And the reason why a red giant does what it does is this kind of vicious cycle that happens as illustrated in this particular slide right here, where when the core runs out of hydrogen and it's got helium left in it, but it's not hot enough to burn the helium yet, gravity is stronger in the core than pressure is, so the core shrinks. If the core shrinks, it converts energy into energy. It converts what kind of energy into what other kind of energy? Gravity energy, gravitational energy, into thermal energy. So the Sun's core will shrink, its helium core will shrink, convert gravity energy into thermal energy so it gets hotter. And as it gets hotter, it heats up the surrounding hydrogen, and that's why there's hydrogen burning in the shell surrounding the core. And it burns very fast because it's at a higher temperature than the core ever was. And meanwhile, all that energy being released by the hydrogen burning shell raises the pressure in the star's outer layers. And so while in the core, gravity is stronger than pressure, in the outer layers, it's the other way around. In the outer layers, because of all the energy released by the hydrogen burning shell, pressure is stronger than gravity. And that means the outer layers are pushed outwards at the same time that the core is shrinking down. So it's the energy released by the hydrogen fusing shell that is causing the outer layers of the star to expand and turn the star into a giant as seen from the outside. Yes?
What suggested the Sun as a protostellar disk?
Yeah, okay. So any questions about what I just did, and then we'll say why the Sun, why we think the Sun has a protostellar disk. Two good reasons for that. One, all the planets in our solar system orbit in very nearly the same plane around the Sun. The orbits have very small tilts with respect to one another. And that's exactly what we would expect if they formed out of a disk that was surrounding the Sun. In other words, the planes of the orbits of the planets is the plane of the disk, the protoplanetary disk that formed around the young sun. So we see direct evidence in that when we look at the fact that the planets have the same orbits. If there were no disk, we would expect Jupiter might have a very tilted orbit relative to Saturn, have a very tilted orbit relative to Earth, and so forth. And the other thing is that we actually see protoplanetary disks around other stars. So, for example, in the Orion Nebula, we actually have photographs that show protoplanetary disks around other stars. So for both those reasons, on top of theoretical calculations suggest that disks ought to form, put it all together, it's like, yeah, there's disks. We have both theoretical reason to think they should exist and observations to say they do exist. And in the case of our solar system, did exist. Yes?
Can we go over the life cycles of low and high mass stars?
Low and high mass stars, yep. So we do a low mass star. Is the sun low mass or high mass? Yeah, for these purposes, it's a low mass star. It's more massive than 90% of the stars out there, but it's still a low mass star for these purposes. It's really saying most stars are low mass stars, is what it comes down to. And so for a low mass star like the sun, remember I said that this figure is very helpful for summarizing everything. So, first off, what's the very first stage in the sun's life? When it wasn't even a star yet, it was a protostar. And then, what stage in its life is the sun in now? It is what kind of star? Main sequence star. So, sun today is a main sequence star, right? And as a main sequence star, where is nuclear fusion happening? Are you asking a question? Or are you just, no. Okay. So, where is the sun having nuclear reactions right now? In the core. And what is the fuel that's burning right now in the sun? Hydrogen. So hydrogen burning in the core is what makes a star a main sequence star. That's where a star spends most of its life. About 90% or so of its life is spent on the main sequence. But eventually the sun's core is going to run out of hydrogen. And then the sun is going to first become a subgiant and then a red giant. And when the sun is a subgiant and red giant, what nuclear fuel is burning and where? It's still hydrogen. It's still hydrogen. Helium is later. So when the sun is a red giant, it's still hydrogen, but is it burning in the core? No, it's burning in the shell surrounding the core, right? So, core of a subgiant or red giant has inert helium, so nothing's happening in the core in terms of nuclear fusion, but there's hydrogen fusion in a shell surrounding the core. So that's the next stage in the sun's life cycle, is subgiant and then red giant, where you've got hydrogen fusion as the source of fuel and an inert helium core. And then climb, getting bigger. This point right here isn't labeled per se on the diagram, but what happens at this point right here? What ends the sun's red giant stage? Helium flash, right. So at this point right here, the helium flash occurs. And then the helium flash is over in a very short time, like seconds to minutes. And then the core expands and cools down. And the core becomes, the sun becomes what your book calls a helium core fusion star, which is a very suggestive name. what's happening in the core of a helium core fusion star? Helium is fusing, right? Yes, very good. Detective work there, yes. Helium is fusing, creating what? Triple alpha process, so it's making carbon, also oxygen, but it's making mostly carbon. So the core of a helium core fusion star has helium fusion in the core, but remember it's also got hydrogen fusion surrounding the core still. So a helium core fusion star, also called a horizontal branch star, because horizontal branch stars occupy a horizontal line on the HR diagram, that's why they're called horizontal branch stars, have two sources of energy: hydrogen fusion in a shell, helium fusion in the core. Now, the core is eventually going to run out of helium, and then we're going to get kind of a repeat performance of what happened when it ran out of hydrogen. Namely, the inert core will shrink, heat up, and cause fusion to continue in shells surrounding it. And so it gets to be what your book calls a double shell fusion red giant. Okay, how many shells have fusion occurring in them in a double shell fusion red giant? 2, yes. And the fuels that are burning are hydrogen in the outer shell, helium in the inner shell, and there's inert carbon core at the inside, because that's what the helium fusion made when it was a helium core fusion star. So it's got a core of inert carbon, no nuclear reactions, surrounded by a helium fusing shell, surrounded by a hydrogen fusion shell. Anybody remember what's the typical astronomer name for this kind of star? AGB, which stands for asymptotic giant branch. Right, asymptotic giant branch star, or double shell fusion red giant. So the sun will become a red giant for the second time. And that's the beginning of the end. It doesn't have long to go, because at that point it turns out the helium fusion shell is subject to what are called helium shell flashes, which shouldn't be confused with helium core flashes, in which it spikes up every few 100,000 years how much energy it's producing. And the floods of energy from the helium shell flashes cause the outer layers of the star to be shed into space, making a lovely planetary nebula. Yeah, so the sun will produce a planetary nebula, which will be relatively short-lived, astronomically speaking, maybe like 50,000 years or so. And then all that will be left behind is the burnt-out core that will be made of carbon and also oxygen, but mostly carbon, that was formed by helium fusion back when it was a horizontal branch, aka core helium fusion star. And that burnt-out carbon-oxygen core will be about the size of the planet Earth and will be called a white dwarf. Yeah, so the sun's final remnant is the white dwarf, which will be the burnt-out carbon-oxygen core left behind after the planetary nebula is shed off into space. And so that's the life cycle of the sun or other low-mass stars. Any questions about any of that? Yes?
So helium fusion causes carbon.
Helium fusion makes the carbon, that's right, yeah. Hydrogen fusion makes helium, helium fusion makes carbon. Does the sun ever fuse carbon? No, the sun will never fuse carbon, so helium is the last nuclear fuel for a low-mass star. But high-mass stars can go beyond that. A high-mass star undergoes a whole series of additional stages of fusion reactions until, when it is doomed, it has reached the point where it has an iron core forming in the center. And meanwhile, it's got a bunch of shells where there's a hydrogen burning shell, a helium burning shell, a carbon burning shell, a neon burning shell, an oxygen burning shell, a sulfur and silicon burning shell, dumping iron onto the core, and that's when it's truly a ticking time bomb, because when enough iron dumps onto the core, we get what we were talking about earlier, where it becomes so massive that even degeneracy pressure can't hold it up anymore, and it collapses, and the tremendous amount of gravitational energy it releases by collapsing blows the star to shreds in a supernova explosion.
So, neutron stars, do they have any radiation of their own?
They're hot enough that they do glow, the surfaces glow, but they're very dim because even though they're very hot, they're very small, and so they don't have a lot of surface area. And also, and then basically I'm going to say kind of, don't worry, that's the next chapter. We'll say more about that.
And they're so densely packed that there's nothing for, I guess nuclear fusion is not exactly an issue there.
Nuclear fusion is not an issue because they're made of neutrons that are not going to fuse. Now, in a binary star system, you can get nuclear fusion on the surface of a neutron star from material that is dropping onto it from the companion.
Yeah.
But the neutron star itself does not fuse. So white dwarfs and neutron stars are both final stalemates in the battle between gravity and pressure. A white dwarf, electron degeneracy pressure holds it up. In a neutron star, neutron degeneracy pressure holds it up. And in both cases, that can last forever, is what it comes down to. No fusion needed to make that statement. Yes?
For the high mass star, do they get to do all the same things as low mass up to red giant?
It basically what happens is that with a low mass star, once you get double shell fusion, that's the beginning of the end. High mass star just keeps on going though. A high mass star, that's not the beginning of the end, because a high mass star's core gets hot enough to fuse carbon and keep things going. Whereas a low mass star, the carbon core stays inert, it never starts fusing. And furthermore, the greater amount of material surrounding the high mass star keeps it from poofing off a planetary nebula. That doesn't happen. The outer layers stay there while all this other stuff is happening on the inside. Yes?
Is the reason that a high mass star gets hot enough because the mass creates enough gravitational...
So a high mass star at all times, it turns out, kind of paradoxically, it's kind of surprising really, but it turns out that that's what you really need for the equilibrium. The density inside a high mass star's core is actually lower than inside of a low mass star, so that its temperature can get higher than a low mass star's does. And so what it comes down to is that the core of a high mass star made of carbon, it does reach 600 million Kelvin, which is what it takes to fuse carbon. The sun's core will never reach 600 million Kelvin because degeneracy pressure will support the core before it ever reaches a temperature of 600 million Kelvin. But in a high mass star, the core isn't degenerate, and so it doesn't stop before it gets to 600 million Kelvin. And so the core gets hot enough to burn carbon, and on and on and on, and burn other nuclear fuels as well. So their cores get hot enough to burn additional nuclear fuels that low mass stars' cores never get hot enough to burn. Yes?
How do open clusters and globular clusters differ in their ages and number of stars?
Yeah, globular clusters are older. Typically, they formed earlier than open clusters did. They formed when the galaxy was much younger than open clusters. And globular clusters have a lot more stars in them. And if you look in the book, I don't have one right here, but if you look in the book at the pictures of open clusters and globular clusters, you'll see their appearances are very different. Globular clusters get their names because they look kind of like globes. They look like globes of stars. And so they tend to have a spherical kind of shape to them, whereas open clusters are more amorphous. They don't have any well-organized structure to them. And globular clusters are, for the most part, all very old, billions of years old. Open clusters show a range of ages. That tells us that globular clusters aren't being born anymore, but open clusters still are. There are very young open clusters. There are no very young globular clusters. Is it happening? Point when everybody's thinking who's going to get up first.
We go
Yes.
over the mass luminosity relation.
Mass luminosity relation says that as mass increases, luminosity increases a lot more, is the rough words to say. So, in particular, roughly speaking, the luminosity is proportional to the mass to the 3.5 powers. So, that means that if I double the mass, the luminosity goes up by 2 to the 3.5 power, which is a lot bigger than 2. And so the mass luminosity relation is responsible for the fact that more massive stars don't live as long as less massive stars do, because more massive stars have more fuel, hydrogen fuel, available to them than low mass stars do, but they more than make up for that greater fuel supply by how much they chug that fuel. They consume the fuel so much faster because, after all, it's the nuclear reactions that produce the luminosity. So how luminous the star is directly related to how fast it's burning through its fuel. Because the luminosity rises a lot faster than the mass does, that means that more massive stars don't live as long because they chug through their larger fuel supply. And the reason there's a mass luminosity relation is because of the fact that stars have to maintain equilibrium, gravitational equilibrium. They have to support their weight with outwards pressure, and in order to do that, more massive stars have to have higher luminosities, higher internal temperatures in order to have enough pressure to support their weight. And nuclear reactions increase very rapidly as temperature increases, and so high mass stars have much more higher rates of fuel burn. So then you get this part where people are thinking, yeah, I kind of want to go at the same time. Maybe they're going to ask somebody else going to ask this really important question that I hadn't thought of. Looks like we will have the observing session, by the way, because there's last check. Yes?
So would tonight count as a non-cloudy?
Yeah, yeah, because it's not going to be at Perkins, first of all. So only at Perkins would we have a cloudy session.
Okay.
So if it's at the student observatory, we're there because it's not cloudy, or at least it's not so cloudy that we can't see stars. So it's definitely not cloudy for us.
Okay.
Yeah.
How long are the observing sessions usually?
I'm sorry?
How long are the observing sessions?
About an hour. Roughly speaking. Roughly.
So are we supposed to have 2 clear ones, or?
You have to have 2, and no more than one of those can be a cloudy Perkins. So the one Perkins session was a cloudy one. So that means you could not combine that with another cloudy Perkins session, but you could combine it with a clear session either at Perkins or the student.
We need calculators.
No, no, you don't. No, you know, sorry. I know it's causing us consternation and sadness, but just cry yourself to sleep and you'll feel fine in the morning.
Is this session at 9:30 or
9:30, yeah, 9:30.